Into the atmosphere of the giant planets, we'll start off with the ices since it's the last things we talked about. Now, one thing you may have noticed is that the ice planets tend to have this bluish tinge, and that's just due to the abundance of methane. Methane's doing a great job of scattering in a blue color. So, on the ice giants, and particularly in Neptune in these pictures here, you're seeing these high clouds that tend to be this methane compounds. On Jupiter and Saturn, the different colors we've seen there, that goes back to the different ranges of chemical compositions there. Doing that familiar game we did back when the terrestrial atmospheres look at the temperature versus altitude. For the gaseous planets, it'll be easier to think about going downwards. So the terminology I'm going to use is that as we go deeper and deeper into the planet's atmosphere, we're going to get to higher temperatures, higher pressures. That's a more defining characteristic. And for the gas giants, we'll find very similar gas layers. These top layers may be a little bit of hydrazine versus diphosphine. But underneath that, you're going to find lots of ammonia or ammonia hydrosulfides and some water clouds. This last one here is another ammonia hydrosulfide. Jumping over the ice planets, there's probably some hydrocarbons and, once again, some methane and hydrosulfide gas clouds. Now, if we look into those gas giants in just a little bit more detail, start bringing back the terminology that we had used before. Let's look at this breakdown. On Jupiter, we'll see that we'll define that zero temperature to be right above what is the equivalent of the troposphere. So a lot of the storms that we are seeing on the surface of Jupiter, that's all happening here in the troposphere. Now, right above that, we'll jump straight into the stratosphere. But once again, for the gas giants, we care more about going down to the planet where the temperature is increasing. And through those, on Jupiter, we'll start to find this layer of ammonia ice, ammonia hydrosulfides, some water ice, and then we start getting down to the gaseous hydrogens and heliums. More methanes, more ammonias, just nitrogen, hydrogens making chemical compounds together. And for Saturn, you'll see this almost similar pattern. Large, thick layer of ammonia ice, followed by some ammonia hydrosulfides, then the water ices. As for the ice giants, our defining characteristic will be underneath this layer of methane ice. And that methane ice, that gives the ice giants their distinguishing bluish tinge. Going through those details a little bit more, you got some hydrogen sulfide ice, ammonias, water, and then just this complex chemistry soup happening. And it's in the methane ice layers that you see the storms, the weak bands in the ice giants. Whereas, going back one slide, the bands on the gas giants, that's what's happening up in the troposphere. One interesting feature of the giant planets is that they're actually hotter than expected. This is predominantly true for Jupiter, Saturn, and Neptune. Uranus doesn't quite follow this pattern. But for these three planets, we'll notice that they have a significant amount of internal heat. They are hotter sources than what we'd predict. Now, a consequence of this is that that heat is going to flow outwards, powering up, driving the storms. Think back to on Earth. Where do all the hurricanes, where all the tropical storms form? They form above the oceans. And what's powering them? It's the warm water. That warm water heats up air nearby, rises that up, and creates that cycling pattern that eventually turns to a storm. So, even on the giant planets, they have some mechanism, something that's powering the internal heat that is driving those long storms. Now, the combination of that heat and the global circulation patterns creates this huge complex interaction, making those wonderful, beautiful pictures of storms on those planets. So, a question we ask ourselves is, hey, if we know they are hotter than they should be, hotter in the sense of how far away they are from the sun, here's the question. We know the giant planets are radiating more energy away than they receive from the sun. what's the source of that internal heat? What is driving this? So go ahead and pause for a second. Come on back. Okay, so here's the discussion topic. Are the cores very hot? Not so much. Is there this gravitational contraction? What the heck does that mean? Absolutely. Let's go ahead and go through this. This all falls under this topic of what we call the Kelvin-Helmholtz mechanism. Here's the concept. You take a big planet, and gravity is still trying to crush it in. And so you take an object and you squeeze it, you crush it down a little bit, it shrinks in size. Well, a small change in radius will equal a big change in temperature. So in essence, what's happening is that gravitational energy, as it crushes the planet down a little bit, is heating up its internal structure. Now, it's not a dramatic amount. We're talking millimeters over the many years. So it's a very slow process, but that tiny change, a small increase of gravitational energy, creates this powerful, large increase in the internal temperature of the planets. Looking at the winds and the storm patterns on the planets, here we have a plot on each of the giant planets. So on the x-axis, we're looking at the eastwardly wind speeds in meters per second. So if it's a negative value, that just means it's gas going in the westerly direction. And then you just scan across the planet. So Jupiter, as we expect, has these huge band structures where you'll have regions of gas going easterly at 100, 150 meters per second. And then you go only a few degrees north, and suddenly it'll be going upwards of 20, 30 meters per second the opposite way. So you'll have this crisscrossing patterns of gases going very rapidly one way, and then just a few degrees north, and they're going westerly another direction. And so the combination of these westerlies versus easterlies creates a swirling vortex. Let's clear that out a little bit. So that crisscrossing is where you see the vortexes, the storms forming on Jupiter. So coming around, Saturn and Jupiter will have the most extreme storms. On Saturn, you'll have wind speeds that are upwards of 300, even as high as 400 meters per second. Similarly on Neptune, though for some reason a westerly direction. So things that we do understand. Recall that every single one of these planets is rotating rapidly. We're talking about a day on Jupiter is about 10 to 11 hours. So you have these rapid planetary rotations producing strong Coriolis forces. Remember when we talked about the atmospheres on Earth? We talked about a section on Hadley circulation. And that's how the gases are flowing from the, say, hot equators upwards around the poles and back down. Well, make it a giant planet, make it nice and gigantic, and you have these big, strong Coriolis forces creating these complex cells, breaking things up. So with Jupiter and Saturn, we do see a lot of these band structures. And they're present on Uranus and Neptune, but like we said, weak banding. There's not as many flips in the direction of the speed. And one of the defining characteristics of all these is that the differences. What makes Jupiter have so many bands, where Saturn doesn't? And Uranus and Neptune have this simple, almost sinusoidal arcs. What's going on there? We don't fully understand the picture. We don't understand these distinguishing features. Looking at the bands on Jupiter in just a little bit more detail, I've highlighted two distinct bands, one going easterly, the other westerly, and they're going almost the same speed in the opposite directions. So let's go ahead and turn on the animation and watch these gas flows fly by each other. Now these were all taken by the Cassini spacecraft, and they're images over about 24 Jovian days, or 10 Earth days. And you'll notice those dark spots that flicker on. Those are just moons getting in the line of sight crossing our field of view. But look at the patterns as they flow by, especially around here. Notice you have some gases coming in and they'll start to swirl around, mixing with gases going the wrong direction. Then you have the great red spot, this giant chaotic storm. So the emphasis here is that the bands, those are Coriolis forces breaking down what's happening in the gases, breaking down how they're going to move around. And when you see structures here, different distinguishing colors, whites, browns, reds, oranges, yellows, this is a sea of chemistry happening right now. A complex sea that's constantly interacting, swirling around.